Hello everyone, I'm honored to introducing our work, D4-VTON, Dynamic Semantics Disentangling for Differential Diffusion-based Virtual Try-On. The goal of image-based virtual try-on is to generate realistic try-on results given an image of clothing and a person image. The try-on results must maintain the person's ID and pose, preserve areas unrelated to the target clothing, and ultimately transfer the target clothing onto the human image. The VTON task has two main challenges. First, warp the garment to fit the human body. Existing methods mainly focus on global alignment, neglecting local semantic changes during deformation, which affects texture fidelity, red box. Second, synthesize realistic results using the warped garment. Diffusion models, unlike GAN-based methods, green box, use conditional guidance for stable training and broader domain knowledge, leading to high-quality results. However, current methods train denoising and inpainting paths with different inputs, relying on ground truth similarity, which introduces learning ambiguity and affects reconstruction accuracy, orange box. To solve these issues, we propose D4-VTON, a virtual try-on model that preserves garment texture patterns and generates high-fidelity results. For the first challenge, we introduce dynamic semantic disentangling modules, which use garment feature self-similarity to learn local flows for semantically disentangled deformation. For the second, we propose a VTON diffusion paradigm that reduces ambiguities from multi-degradation recovery and improves overall performance through differential information tracking. Here is our pipeline, which adopts a two-stage framework for the virtual try-on task. In the deformation network, we first input the clothing image G and the conditional triplet O into a feature pyramid network. The extracted features are processed by dynamic semantics disentangling modules to obtain the masks used for grouping, as well as the corresponding flows and attention maps. These are then used in the disentangled warping operation to warp L0, resulting in the warped clothing G omega. In the synthesis network, we introduce a differential information tracking path to optimize the inpainting process, ultimately generating the final try-on result I hat. Our DSDM includes three key components. 1. Dynamic semantic selector, which uses the self-similarity of garment features to unsupervisedly generate selection masks indicating each channel's semantic group. 2. Group warping block, which cascades a coarse estimator and a fine estimator for coarse-to-fine flows estimation. And 3. Disentangled warping operation, which applies different local flows to deform each semantic group based on the following formula. In the synthesis stage, to minimize learning ambiguities caused by multi-degradation restoration, DITP captures the differential information between the latent code ZT and its incomplete counterpart ZT' to separate the denoising and inpainting tasks. We evaluate our method on two widely used benchmarks, VTON HD and dress code datasets. In the paired setting, D4-VTON outperforms the second-best method by 0.7 dB in PSNR and 0.004 in SSIM, indicating more accurate garment warping and try-on results. Additionally, in the unpaired setting, our method shows strong generality, improving FID by 0.224 and KID by 0.43 compared to the second-best approach. Here are the qualitative results on the VTON HD dataset. D4-VTON applies multiple local flows using dynamic semantics disentangling, leading to more accurate warped results. Additionally, the DITP design helps reduce the gap between incomplete and complete latents, easing the challenge of restoring multiple degradations. This results in more realistic and garment-consistent try-on outcomes. The following figure presents the results on the dress code dataset, with categories arranged from top to bottom as upper body, lower body, and dresses. We conduct ablation studies to verify the effectiveness of various components. Figure 6 shows the fine attention map from the last DSDM for different groups. Specifically, Group 2 captures global garment information, Group 5 identifies patterns, Group 7 focuses on garment contours, and Group 8 includes supplementary details. To demonstrate the effectiveness of DSDM, we use three different settings. In the fixed grouping setting, channels are evenly divided without the dynamic semantic selector, as shown in the upper part of Table 3. We also provide a qualitative comparison of warped results against DCI-VTON and GP-VTON in Figure 7. The effectiveness of DITP is evident in the lower part of Table 3. The setting, with DSDM and DITP- refers to using DSDM without the denoising path, while, with DSDM and DITP, represents our full model. The former improves performance in the paired setting but underperforms in the unpaired setting, highlighting the denoising path's role in enhancing generality. Both settings with DITP show significant improvements over other variants, validating its effectiveness. Thanks for watching.